Okay, we are going to look at the inverse of a square matrix. Okay, very, very interesting component. Just like you can find the inverse of a function, a matrix also has an inverse. Only square matrices, though, are invertible, and not all square matrices do have an inverse. Now, we saw that when we spoke about the determinant earlier in another video. We saw that if the determinant was naught, there cannot be an inverse for this matrix. So let's see why that is indeed the case. Okay, so if I have two matrices, A and B, and I multiply them with one another and I get the identity matrix, then I have A and B as each other's inverses. Now, so you can remember the composition of functions. If you take a function f and you determine its composition with its inverse, its result will be x. So fx composed to f inverse x gives you an answer of x, and that is because there's that symmetry in the line y equals x. Now the same is going to happen with the work we're going to look at here. An n by n square matrix is called invertible if there exists an n by n square matrix B. So first of all, n by n square matrix A, n by n square matrix B, such that this holds true. The product of A and B with B is going to be the same as the product of B with A. We'll see that later on. And it gives you the identity matrix. Okay, so that IN represents the identity matrix once you have multiplied the two matrices together using matrix multiplication. A square matrix that is not invertible is called singular or degenerate. That's quite harsh. Okay, so a square matrix is singular if and only if. When is it non-invertible or singular or degenerate? When the determinant of that matrix is 0. Don't forget. So non-square matrices, M and N, M by N matrices, where M is not equal to N, do not have an inverse. It's only the square matrices that has an inverse. Okay, so how do I find the inverse of a square matrix? What do we do? Well, we're looking for a matrix B which satisfies that equation. Okay, the inverse B can be written as, like in function notation, A, and that's not to the power of -1. That just is the notation when we talk about an inverse. Just like you did when you spoke about the function f, -1 in the index of the f is represented not 1 over f, but the inverse of the function f. If you work in normal algebra with x to the -1, then that is 1 over x. But we're not representing a number here. We're representing an object called a matrix, like we represented an object called a function. Okay, so when A is multiplied with its inverse, the result will always be the identity matrix. So that's a fact, folks. Whether you multiply A with A inverse or A inverse with A, the result is always going to be the identity matrix. So, an invertible matrix theorem, we say it's invertible or non-singular if the denominator or if the determinant of the matrix is not naught. Now, you've heard that quite often, so that should sink in quite well. If the square matrix is not invertible, the determinant is 0. So how do I determine if a matrix is invertible? Well, simple. You find the determinant of that given matrix. If the determinant is not equal to 0, it is invertible. Okay, so let's look at those two matrices at the top. A 2 by 2 matrix and a 3 by 3 matrix. The determinant of the first one, we say 3 times 4 is -12. We say 5 times 2 and we subtract it from the -12, so the result is -22. It is an invertible matrix. Okay, if we use the augmented way to find the determinant of B, 1 times 2 times 4 gives us 8. 3 times 6 times minus 9 gives minus 54. Minus 2 times 2 is minus 4 times 5 gives us minus 2. We subtracted from 3 times 2 is 6 times 4, which is 24. 1 times 6 times 5 is 30. And 2 and that minus 3 gives us positive 6 times 2 is positive 12. We put the second grouping in a bracket, we add them, and our determinant is minus 132. Okay, therefore the matrix is indeed invertible. So both are non-singular because the determinants are not naught and are therefore invertible. Okay, how do we find the inverse of a 2 by 2 matrix? Now this is the point where you maybe want to take out a pen and take some notes as we continue. We're going to use some new terminology and facts about matrices. The first thing we want to talk about is the adjoint of a matrix. The adjoint of a matrix A is the transpose of the cofactor matrix of A. It is denoted as ADG of A. An adjoint matrix is sometimes also called the adjugate matrix. Now folks, there's a lot of words in that sentence that you haven't heard before. So let's see. The transpose, we know the transpose of a matrix is just you simply taking a matrix columns and making them rows in the next matrix. So we swap the rows, they become columns. This row becomes a column, or that column becomes the first row. The second column becomes the second row. So we just interchange the rows and columns of matrix A and we have its transpose. The cofactor matrix of A is as follows. The determinant obtained by deleting a row and column of a given element of a matrix. Okay, please, we're going to find the determinant by deleting rows and columns. The cofactor is then preceded by a plus and minus sign depending whether the element is in a positive position or in a negative position. Now folks, that's a mere definition. We're going to work with that and you'll see exactly what it means. We will pay attention to this later, therefore, when we come to the when we find the actual inverse for the square matrix. Okay, so let's see. We want to find the inverse of a matrix P and we want to introduce more formal concepts. So let's have a look here. That is how we're going to find the inverse. We're going to use the determinant, we're going to turn it on its head and then multiply it with the adjoint matrix A. How do we do that? Well, we're calculating the matrix of minus, then turn it into the matrix of cofactors, then the adjugate, and then we multiply it with the reciprocal of the determinant. Let's look at that very easy 2 by 2 matrix. Now remember, we said we're going to cover rows and columns, so follow carefully. We're going to find the matrix of minors. Okay, so the matrix of minors are going to have these 4 entries. Okay, so if I want the first entry over here, then I need to cover that row and that column. I cover them totally and my matrix of minors in that position will have the number that's left, and that is the number 12. So the entry in the matrix of minors in the position M11 is 12. We do the same for M12. That means row 1, column 2. So we're going to cover row 1 and column 2, and the entry will be 6, as we see over there. Okay, let me just get rid of those markings because I'm going to move all of this around in a few minutes. Okay, so the third one that we want to find is M21. So we are now at this entry, meaning we're going to cover that, and this becomes the minor. What's left becomes the minor, the entry over here. So we cover We add this entry, we cover that column, this row. So the entry M21 is what remains in the 2 by 2 matrix and is therefore -3. The same for the fourth one. We cover. We want to find this entry, so we cover that row, that column, so the entry is going to be 2. Now folks, if we bring all of that together, there's all my minors that I calculated. If I put it into a matrix, that is what the matrix of minors is going to look at, or look like. Okay, the second step is to find the matrix of cofactors. Now let's see. We use our matrix of minors, then we change the sign. So it's almost like you're saying there's a plus. I'm going to multiply it with a plus, so it leaves a positive. There's a positive, I've got to change to a multiply with a negative, so it becomes negative. There's a negative times that negative makes that positive, and this positive times that positive gives me a positive 2. So the only sign that changed here is the sign of the 3 and the sign of the 6. That's going to become important later on. Okay, now let's just stand still at this point. If we look at our initial matrix up here, the matrix at the top of the page, that was 2 and this was 12. So it seems along that diagonal, those two entries changed their position. It's now 12 and 2. Okay, and what happened to the next one? They changed, and they changed sign. Now let's see if that is indeed going to be the case going forward. So far that's what we've got. Okay, that is what we have. We have the matrix of cofactors. Okay, so now we want to find the adjugate matrix or the adjoint matrix. Well, how do we find it? We use the transpose of the matrix of cofactors. So this column is going to become that row in the matrix or in the adjoint matrix, and this column is going to become the second row. Okay, so there we have it. 12, 3. The first column became the first row in the adjoint matrix. The second column became the second row in the adjoint matrix. And we have our adjoint matrix. We are ready to find the inverse. All we need is the determinant, which is rather easy. 2 times 12 is 24 minus 18. We add the 2 together and we get a determinant of 42. So we are going to use our formula. We're going to reciprocate the determinant and we're going to multiply it with the adjoint matrix. If we do that, we get something that looks like that. Now that is your inverse matrix. Very important. Okay, so there was a few steps that we had to follow. We had to find the matrix of minors. From that, find the matrix of cofactors, which is literally just changing signs. Then the adjugate was the transpose of the matrix of cofactors. We find the determinant, we reciprocate it, and we multiply it with the adjoint matrix, and it gives us our inverse. Okay, so in general, let the matrix entries be A, B, C, D. Is it invertible? Well, we quickly check the determinant. If it's not 0, then it is invertible. Okay, so to be invertible, the determinant is not 0. To invert the matrix, we then use two things. We use the determinant, which is turned on its head, and we use the adjoint matrix there at the bottom. Now let's inspect here. The original matrix had an A and a D there. The adjoint matrix has a D and an A. So AD became DA. Okay, so those two entries swapped around, DA. These two entries just changed their sign. They still remained in the same place, but they changed their sign. Let's see if that is true for the... No, let's continue. Okay, so after that, we then used our inverse product, our inverse, forming our inverse matrix, we use the product of those two things we calculated. Now, how did we find the adjoint matrix again? Find the matrix of minors, find the matrix of cofactors using the sign changes as indicated over there, then find the transpose of the cofactor matrix, and you have the adjoint matrix. Then you can multiply them together. Okay, so let us see if you can find the inverses of those 2 by 2 matrices. There's 4 of them there. Let me do the first one with you, and then you can do the remaining 3. Okay, so that's what we're going to use to find the inverse with. So for matrix A, our determinant is the first thing we found there. 2 times 3 is 6. Minus 4 becomes 6 plus 4. Determinant is 10. It's an invertible matrix because it's not 0. Okay, and then the 3, 1 minus 4, 2. What happened? Well, we said we interchange those two. The 3 goes where the 2 is, the 2 goes where the 3 is, and we change those signs. So we go for the adjoint matrix straight away. 3 and 2, a minus 1 becomes a plus 1, a plus 4 becomes a minus 4. And from that, remember now folks, we interchange from matrix A. To find the inverse in the adjoint matrix, we interchange those entries. Those stay the same, we just change their signs. Now we're ready to multiply the two together. If we multiply them together, we get a rather strange looking matrix. We're not going to simplify that. We're going to leave the denominator to 10 because we're going to multiply, or you'll see why now. Let's see if it is indeed the inverse. If I take matrix A and I multiply it with its inverse, I want to find the identity matrix. Okay, so let's see if that's the case. If I do that product, okay, what do I get? I get 2 times 3 over 10, which is 6 over 10, plus 1 minus 1 times minus 4 over 10 makes it plus 4 over 10. Now that already we can see is 1. The entry over here, we get 2 over 10 minus 2 over 10. Which is not 12 for the entry over here, that entry. It's this row multiplied by that column. So 12 over 10 minus, or rather plus, the product of those two, which is minus 12 over 10, gives us 0. And then for this entry, it's 4 times the entry over there. So it's 4 over 10 plus 3 times that is 6 over 10. Now folks, I don't even have to do the sums for us. We can see that that is the identity matrix. Okay, so you're going to do the same for B, C, and D and check if your answers are correct. So at this point, pause the video and then come back and see if you've got the thing correct. Okay, let's have a look at the second matrix. We found the inverse by doing what? By interchanging 1 and 1. Well, if you interchange 1 and 1, it stays 1 and 1. And then changing the signs of 2 and 2 to find the adjoint matrix. So that signs just changed to negatives, both of them. The determinant was 1 minus 4. Now 1 minus 4 is minus 3. Okay, so we have minus a third multiplied by this matrix, and it gave us that matrix that's filled with fractions. Okay, let's see what you did for C. For C, the same thing. 4 and 2 for the adjoint matrix. 4 and 2. Now remember this notation just saying I'm taking this matrix, I'm inverting it. Okay, so the adjoint matrix will have 2 and 4. There's a 1 and an 8 is now a minus 1 and a minus 8. I have 8 minus 8, and look at this. This is a visual thing for you to see why the determinant can't be 0. Because there you have an indeterminate multiplied by something. That just doesn't make sense. That is why this is a degenerate matrix, because its determinant is 0. Its inverse does not exist. Okay, the last one is the identity matrix, and as expected, the identity matrix's inverse is just itself. Okay, folks, remember the determinant of the identity matrix is also 1. We saw that in a prior video. Okay, that takes care of the 2 by 2 matrices. There's another one for you. Find its inverse and show that the product of P multiplied by its inverse is the same as the inverse multiplied by the initial matrix and gives the identity matrix. Pause the video now, do the problem and come back. Okay, let's see. For the determinant of P, it makes sense to find that first. You found the determinant by excuse me, 2 times 24, and you subtract that from 3 times minus 3 times 6, so that double negative makes it a positive. Determinant is 42, so we're going to use 1 over 42. Okay, and then you multiplied by the adjoint matrix, which you found by interchanging those 2 entries and changing the signs along that entry, and there's your final result for the inverse of this matrix. Okay, now let's see. The matrix multiplied by its inverse. You should have gotten this. You should have gotten the identity matrix. Okay, so you do your normal matrix multiplication. You do be very careful of signs, folks, and be very careful of fractions. That is where errors happen in matrix algebra, is a simple negative that you do not see that changes the whole outcome for you. And then the other way around, you do the same thing, you see that you again get the identity matrix. So not so difficult, it's a 2 by 2 matrix. Okay, so find the matrix where we find the inverses of those 3 matrices and then show that those are the same. Okay, pause and quickly do that. Okay, let's see what you did. We're just going to put the final answers on the screen. The answers for the first inverse, minus 7, 3, 5, and minus 2. The second P, the inverse looks like that. And for the third matrix, the inverse does indeed look like that. And I'm sure you got all of that right. If you did not, just go back and check for multiplication errors where there were fractions or for signs that you did not use correctly. Okay, let's look at the inverse of a 3 by 3 matrix. Okay, let's have a look how this works. Well, first of all, there are many ways to find the inverse of a 3 by 3 matrix, but we will start by using cofactors and minor matrices, just like we did for the 2 by 2. Okay, to find whether it exists, we quickly look at the determinant of this matrix. We augment the matrix, we find the determinant, we see the determinant is minus 96, so definitely the determinant or the inverse of this matrix exists, because the determinant is not naught. Okay, since it's not naught, it is invertible, so we go back. Now remember what we did for the matrix of minors. We covered rows and columns, and we worked our minors like that. So there's my 3 by 3 matrix of minors. Now remember the entries here in the subscripts is row 1, column 1, row 1, column 2, row 1, column 3. This is row 2, column 1, row 2, column 2, and so forth. So let's start our calculation. We're wanting to find this first entry over there. Now follow carefully, folks. You cover the row and the column where that entry intersects, and you find the determinant of what remains. So the entry M11 will be the determinant of that little 2 by 2 matrix, which is 93. It's quite different from what we had when we worked with a 2 by 2 matrix. The second entry, row 1, column 2, means we're going to cover the minus 2, the row in which it is and the column, and we find the determinant of what remains, which is 6. Entry 1, 3, row 1, column 3. Row 1, column 3, we're working here, so we cover that and this, and we find the determinant of what remains, and it's minus 67. So there we have our very first row of our matrix of minors. It's going to be 93, 6, and minus 67. Let's continue. We move to row 2, column 1. So this entry over there. We cover the row to which it belongs and the column, and we find the determinant. We do the same for entry 2, 2. We cover that column and this row, and we find the determinant of what is left. The same for M2, 3, which is the third one. We cover the row, we cover the column, we work with a determinant, and then we have the matrix of minors, the second row for that matrix of minors. It's quite some time, but the more you do this, you'll train your eye, and you'll do it far quicker. The first time you see it, it looks a little bit complicated. Row 3, column 1, cover, cover, work out the determinant. Row 3, column 2, we cover the row, the column, we get that, we work the determinant, and the same for the last entry, which is 3, 3, and we will cover and find the determinant. Okay, so that sort of gets us to our matrix of minors, which we see here at the bottom. Now we have our matrix of minors. Now what follows? The matrix of cofactors. Now, like this, the 2 by 2 matrix was minus plus, or plus minus minus plus, the same happens over here. We start with a plus and we alternate. So plus minus plus, then a minus, a plus, a minus, plus minus plus. Now where there's a positive and a positive, the sign will not change. Where there's a positive and a negative, the sign is going to change. So, and where there's a minus and a plus, here the sign is going to remain a negative. And you go through, that's going to be a positive, this is a minus, that also becomes a minus. That remains a minus, this becomes a minus, and that remains a minus. So once we've done that, we see what our matrix of cofactors look like. Okay, so it's merely just the signs that are changed. So there's our matrix of cofactors. Now we need to find the adjoint matrix. Now remember, how do we find it? We find the transpose of the matrix of cofactors. Okay, so for the adjoint matrix, we just make the first column there the row in the adjoint matrix. The second column becomes the second row. Third column becomes the third row. Or your first row becomes your first column. Your second row becomes your second column. You interchange the rows and the columns in the matrix. And now we are ready to apply our theory. Okay, let's have a look. Remember, our determinant was minus 96, so we invert it and we multiply it with our adjoint matrix to get our final inverse matrix. Now folks, you can take some time, multiply A with its inverse, and see indeed if you do get the identity matrix, which is what you are supposed to get. Okay, so inverting a 3 by 3 matrix. Okay, we find the matrix of minors, the cofactors, and the adjoint or the adjugate matrix. So step 1, you calculate the matrix of minors by covering columns and rows and finding determinants. Then you adjust the signs to find the matrix of cofactors. Remember, start with a plus in the top left and then alternate. Okay, then you start with a minus, alternate. Start with a plus in the third row and alternate, and multiply and change the signs. Then you get the adjugate, and finally you find the determinant. Actually, you start with finding the determinant, because if the determinant is naught, you're wasting your time. So that should actually be the very, very first thing that you do, is finding the determinant to see, am I going to waste my time? Okay, so there's 2 matrices for you. I want you to find the inverses of both of those matrices and then unpause the video and see whether you were correct. So pause now and quickly do those 2. Okay, so let's have a look. Did you do the right thing? Your first matrix P has this as as its inverse. Okay, so if you did not do that correctly, go back, work very slowly, cover your columns and your rows and see whether you found the correct determinants for the matrix of minors. The rest of it is really plain forward. That is the difficult step, or the step that takes a lot of time. Okay, so the determinant should have been minus 34, and your adjoint matrix should have been the matrix down here. If that wasn't your adjoint matrix, then you made some silly error somewhere along the line. For Q, the same thing. From the given matrix, there is its inverse. Okay, if you did not get that, folks, go back, work slowly. Did you get a determinant of minus 60? If not, that might have been where the error came in. If you did, well done. Your adjoint matrix has to look like that. If it doesn't, go back. Start with your matrix of minors. That is usually where there's an error in your calculations. Think of it. The rest of it is just changing signs and finding a transpose. So the matrix of minors is the key step in your work. Okay, that takes care of our inverses of 2x2 and 3x3 matrices. Folks, if you learned something, please like the video, share the video, and subscribe to my channel.